Right now, petabytes of data are rushing through global networks. To get where it's going, that information constantly hits a physical wall, an interface where an electrical signal in a copper wire is instantly converted into a pulse of light, firing down an optical fiber. The specialized subfield of physics focused entirely on crossing that exact boundary is called optoelectronics. To make this jump, we rely on specialized components that emit light, can detect it, or control its flow. You cannot build these components out of standard metals. They require semiconductor materials, which provide the precise physical medium needed to bridge the gap. Pure electronics is the business of moving electrons. Pure optics is the business of moving photons. Optoelectronics is the translator sitting directly between the two. To engineer our modern communication grids and solar energy arrays, studying standard circuits isn't enough. We have to master the quantum-level exchange between light and solid matter. To understand that exchange, we must define what light actually is. In the strictest physical sense, it is a form of visible electromagnetic radiation. As it travels through space, it moves exclusively in the form of propagating waves. In a vacuum, these waves travel at an absolute constant speed, which physicists denote with the letter c. That velocity is exactly 300 million meters per second. It operates as a hard, fundamental speed limit of the universe. Because that speed is locked, engineers cannot speed light up or slow it down to encode data. The only variables we can actually manipulate in an optoelectronic system are the wave's frequency and its physical wavelength. This chart shows the entire electromagnetic spectrum. The sequence ranges from low-frequency radio waves on the left up to high-frequency gamma rays on the right. Out of this vast expanse, the light we perceive occupies only a tiny fraction in the center. The visible spectrum is a continuous gradient. Each color corresponds to a specific wavelength. Red light sits at the longer end, peaking around 740 nanometers. Violet light features much shorter wavelengths, dropping to 380 nanometers. This physical geometry directly translates to power, governed by the core equation E equals h nu. Since h is Planck's constant, a direct relationship exists between energy and frequency. A higher frequency, a shorter wavelength, guarantees a higher energy state. In engineering terms, color is a precise mathematical measurement of a photon's energy, dictating exactly how hard it will hit the atoms inside a semiconductor. To see that impact, we have to scale down to the atomic structure of the semiconductor material itself. This simplified diagram models two energy bands within an atom, a resting lower energy state and an elevated higher energy state. We start with a single electron sitting quietly in its baseline, lower energy band. The first primary interaction occurs when a traveling wave, a photon, strikes this resting electron. In that split second, the wave's energy is completely transferred and consumed by the matter. Saturated with that new energy, the electron instantly jumps across the gap to the higher energy state. This is known as stimulated absorption. This physical capture of incoming light creates an immediate electrical change. It is the foundational mechanism that allows a solar cell to generate electricity, or a photodiode in a camera sensor to detect an image. We can also run the process in reverse. Here is the exact same atomic model, but starting with an electron that is already occupying the higher energy band. This elevated state is physically unstable. An electron cannot remain up there indefinitely. The laws of thermodynamics dictate that it naturally wants to shed that excess energy and return to its baseline. Without any external prompting, the electron simply drops. As it falls back down, it ejects that stored energy outward in the form of a brand new photon. This is spontaneous emission. The exact amount of energy the electron loses during that specific fall determines the frequency of the newly generated photon. Returning to E equals h nu, the size of that energy gap directly dictates the color of the light produced. Because these drops happen completely unprompted, the resulting light is chaotic. The photons fire off with completely mismatched phases, traveling in random directions. This uncoordinated, multi-directional spray of photons is the exact mechanism lighting up every standard LED screen and indicator bulb you interact with daily. The third interaction requires a highly specific engineered environment. We begin again with an electron suspended in the high-energy state, waiting. The crucial trigger here is a secondary photon approaching the atom, carrying an energy value that perfectly matches the gap between the two bands. When this perfectly tuned wave collides with the excited electron, it forces the electron to instantly drop down. This is stimulated emission. The incoming photon survives the collision, and the dropping electron ejects a second photon directly alongside it. These two outgoing waves are perfect clones, completely identical in their physical wavelength. Because the original wave forced the interaction, both photons share the exact same phase and travel parallel in the exact same direction. They exhibit complete coherence. In physics, this process stands for light amplification by stimulated emission of radiation. This synchronized generation of identical photons provides the extreme directional focus that defines laser light. We can map these three invisible quantum interactions directly onto the industrial hardware that runs our infrastructure. Optoelectronic devices are divided into emitters, detectors, and transducers. LEDs slot neatly into the emitters column. They are physical housings designed to facilitate spontaneous emission. Laser diodes are also emitters, but their architecture is built strictly to trigger the cloned, coherent light of stimulated emission. On the receiving end, standard photodiode detectors and large-scale solar cell transducers rely entirely on capturing waves through stimulated absorption. Despite the vast difference in how a solar panel and a laser pointer look, they are simply different architectural housings designed to force one of these three specific atomic interactions. Every piece of optoelectronic hardware relies on the ability of semiconductor electrons to absorb incoming energy or release it back into space. Every single one of those microscopic transitions is mathematically bound by Planck's constant and the frequency of the wave itself. Modern engineering is the science of manipulating the physical geometry of a semiconductor block to heavily favor either the absorption of a wave or a very specific type of emission. We build these components to move data and power seamlessly back and forth between electrical grids and optical arrays. That reliable translation is what sustains high-speed global internet routing, digital imaging, and the renewable energy sector. Mastering optoelectronics requires looking past the physical circuit board. We are designing the intersections and acting as traffic guards for the quantum exchange between photons and matter.